I'm going to start a new video series on moderators and interaction. In this video, I'm going to provide you an overview of what interaction is all about, what we mean by moderation, the difference between those two, and as you can see, I have subtitled this presentation, When It Depends, which I will explain in a moment. Then we'll go into an example in which we look for interaction and we will find none, spoiler alert. And then we will go to another example so that you can see what it's like when we have interaction. And then I will take on my challenge to create a report in which I investigate the possibility of interaction or moderation. So that's what I'm going to do in this video series. You'll get 3 good examples, but in this video, we're just going to look at an overview of the topic and what we mean by moderation and interaction. Consider the question, the research question, does motivation influence academic achievement? Let's say that it does. Let's say that the answer to our question is yes, motivation does influence academic achievement. Then the next follow-up question that we should naturally ask is, how strong is the effect of motivation on academic achievement? When I do a research study, I don't want to just give a yes or no answer. I'd like to know something more. Specifically, how large is the effect? So how strong is the effect of motivation on academic achievement? And suppose you have to answer, it depends. On what? Well, it depends on the amount of interest in the content. Or perhaps it depends on time spent in the study of that content. Or perhaps it depends on prior learning. When we answer the question, how strong is the effect, with it depends, we are referencing an interaction. We are stating that there is an interaction among some variables in our study. Interaction and moderation. When the influence of one explanatory variable on the response variable depends on the value of a second explanatory variable, the 2 explanatory variables are said to interact in the effect on the response variable. So going back to the examples, when we said it depends on the amount of interest in the content, the question was, how strong is the effect of motivation on academic achievement? And so when we say it depends on amount of interest in the content, we are saying that amount of interest, which becomes one explanatory variable, is interacting with our primary explanatory variable of interest, which is motivation. In the second example, we're saying that motivation, again our primary variable, is interacting with another explanatory variable, time spent in study. And these are interacting in terms of the influence on the response variable, which is academic achievement. When changes in one explanatory variable are causing changes in the effect of another explanatory variable on the response variable, the first explanatory variable is called a moderator. So this might seem like a subtle difference, but I don't refer to all interactions as moderation. Just like I don't talk about all correlations as being causal. Causal is a special case of a correlation. Causal is when not only is there an association, but the reason we have an association is because variation in one variable is causing variation in another variable. It is a special case. You cannot have causation without association, but you can have association without causation. Similarly, we cannot have moderation unless we have interaction, but there could be interaction without moderation. Going back to our examples again, let's look at this first example. It depends on amount of interest in the content. If the amount of interest in the content is what is causing there to be a different effect of motivation on academic achievement, then we would say that interest is a moderator. On the other hand, it may be that there's another variable that we're not even thinking about, that's not included in our model, that is influencing both interest and motivation. In which case, if we see that it depends on amount of interest in the content, we would say there's interaction, but we wouldn't necessarily consider interest to be the moderating variable. There might be something else going on that is not in our model, something behind the scenes. Here's what interaction would look like. Now, in this particular example, I'm using the amount that a couple is in love. I've measured this with a love index, where higher values of the love index means that the couple, let's suppose that it is a dating couple, they are dating each other, and they have fallen in love. And the greater the love index, the stronger the love attraction that they have. And these couples that I'm looking at like to take walks in the park. So the question becomes, how does the influence of the love index affect the number of times that I will find the couples walking in the park? And so what I'm expecting is that, yes, love index, love that is related to the number of times you take a walk in the park. The higher the love index, the more times walking in the park. So as this variable here increases, I expect to see an increase in this variable here. So I ask the question, all right, since they are related, how strong is the influence of love on number of times you walk in the park? That is, how steep would the regression line be? What's the slope? If you answer, it depends upon what the temperature is outside, then temperature is interacting with the amount of love in order to influence the number of times they walk in the park. And let's take it a step further and say that temperature is actually a moderating variable, meaning that it is indeed the temperature that is causing the differences in the effect of love for number of times that the couple can be seen walking in the park. So if we have a 75 degrees Fahrenheit weather, we find that as you look at different couples with different love indices, that what we find on average is that as the love index increases, that is, as we move this way horizontally, that we get an increase vertically, and that increase has a particular steepness or slope to it. And this slope would tell us how many times increase there is in walk in the park for on average, how many times increase there is walk in the park on average for every unit increase in the love index. So we would see how much of a gain we have in times walking in the park for a gain in love index. And that steepness of the line I see here for 75 degrees is in fact greater than it is down here for 35 degrees Fahrenheit. When it's 35 degrees Fahrenheit, the line doesn't actually become horizontal. It's not like the couples all stay home, but they're more likely to not be much change down here when the love index is 2 or 3 or 4. On the other hand, if the love index is 10, those couples are still going out and taking walks together hand in hand in the park. So the steepness of the line with 35 degrees Fahrenheit is not as steep as it was with 75 degrees. That is, the amount of effect that love changes in the love index, the amount of effect that changes in the love have on the number of times that the couples will walk hand in hand in the park, that effect depends upon the temperature. It is not as great of an effect for 35 degrees as it is for 75 degrees. So if I asked you, how does the amount that the couple is in love affect the number of times that they're walking together in the park, you would answer, it depends. And I would ask, what does it depend on? And you would say, it depends on the temperature. And if, in fact, the temperature is moderating the relationship of love to walking in the park, then temperature is actually the influencing factor. And where do we see that influence here in this picture? We see that influence because there is a difference in the slopes of these lines. There is a greater slope here in 75 degrees than there is down here in 35 degrees. Interaction in multiple linear regression models. That's present when the regression coefficients for one explanatory variable are different for various values of a second explanatory variable. And the way we can detect this is by including a cross product in the regression model. Here's what I mean by a cross product, right here. So if we take the two explanatory variables and multiply them together in our regression equation, the value of the coefficient would help us understand whether or not we have interaction. So this first slope coefficient, disregarding the intercept here, so this first slope coefficient here is for the effect, the average effect of x1 on y. We call that a main effect. And the second one is also a main effect. It tells us how much there is an effect of x2 on y. The third coefficient, because it's associated with this cross product, tells us the amount of interaction. If there is no interaction or very little interaction, we would expect beta 3 to be relatively small. If there is a lot of interaction, we expect it to be larger. Now, how do we deal with main effects when there is interaction? Well, think back to the picture we were just looking at. You would have to say it depends when we talk about effects. And what would a main effect be here? A main effect would be an effect without regard to the temperature. That is, looking at the relation of love to number of times walking in the park, and it might look something like my red line here, and we wouldn't even know about these lines. That would be the main effect. That is, we're ignoring that there's an interaction of temperature and love on the number of times couples are in the park. So because of we're ignoring that, when we answer what is the main effect, note that we would give a value that doesn't make a lot of sense. It might be a value that would apply for some temperatures, something between 35 and 75, but it would not be the correct value for when it's 75 degrees out, and it would not be the correct value for when it's 35 degrees out. Why? The answer, it depends. It depends on the temperature. So to talk about main effects as one number, which is what we would be doing here if we were looking at the main effect of, say, beta 1, if we were just talking about that main effect of beta 1, when in fact beta 3 was substantial, then in fact we would be giving a misleading impression, because we would be giving a sort of average effect instead of the specific effect that we could find by looking at various temperatures when we're actually doing the study. If interaction is negligible, then we can remove it from the regression model. So if we have back here, we do an exploration of this interaction, we find that the beta 3 is almost zero, approximately zero. Then what we can do is take interaction out and rerun the model. If interaction is present and substantively important, the effect of an explanatory variable should only be interpreted when conditioned on the interacting explanatory variable. What do I mean by conditioned on the interaction? The explanatory interacting variable? Well, go back and look at this picture. That's what I've done here. I have made an effect conditioned on 75 degrees and another one conditioned on 35 degrees. So that is, you can find values of the moderating or interacting variables to condition on, and then you can talk separately about the individual effects. As with all estimates, the most difficult situation occurs when the interaction regression coefficient is unstable. Suppose that we actually find that we are estimating that there is an interaction, but we have a fairly large standard error for that interaction, and subsequently we have a relatively large p-statistic for that interaction. Then we have interaction in our sample, but we're not sure if it actually would be there if we were to take another sample. It's not a real reliable effect that we can count on. So what do I do in that case? Well, I would certainly note the sample effect. That is, I would note that there was an interaction in my sample. But I would also note that it's not very stable. And so what we might want to do is note it's in the sample, but then remove it and talk about what effects are like if there is no interaction. We would have to give clear cautions, and we would certainly recommend future study.